So if we have some curve C, and it has any number of points, but we would like to find the equation of a line that's tangent to this curve at this point P, what we can do is we can use the knowledge that we have to construct a set of parametric equations that defines a line that goes through that point. And so this being the tangent vector. So this is a more formal write-up, and it basically follows this algorithm. It says, if I've got some sort of point P, then I need to find, and I've got some sort of position vector valued function R, I need to find the time or the whatever such that R at that time equals to P. And then what I can do is, since I now have the time that I'm interested in, I have the time that I'm at P, I can find R prime at T0 and figure out what type of vector I'm dealing with. Now you might ask yourself, why am I not using T at T0? Why am I using R prime? Well, the answer is because R prime is actually parallel to that. Remember that the tangent vector is just a unit vector. So R prime gets you this vector, and the unitization of it, or there's a term for that, normalization, that's the word. The normalization of it shrinks it to a unit vector. But we don't have to have a unit vector. If you recall, going back to the several sections before, any vector parallel to that direction vector for the line is sufficient to construct equations for a line. So really we're just saving ourselves a step. So if I get the values here, then I can construct these equations that x is the line that goes through the point plus the vector times time. And that's really it in terms of that. And we're going to do some examples so that we can sort of, get our feet wet on using this algorithm.